Hello, in today's video we're actually going to be recapping section 6.3. There will be a part 2 to this video as well, and this is to hopefully clarify some of the concepts that were in our first videos on section 6.3. So this is just going to serve as a summary of what's already been talked about. So we've got 6 trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. All these are they are taking the relationships between two sides of a right triangle and finding the ratio between those two sides. The ratio between any two sides of a right triangle is always constant. It's the angles that determine the constant value. So if I am looking at this angle here, theta, the ratio between the opposite side of that angle, theta, and the hypotenuse of our triangle is always going to be a constant, and that constant is the sine of theta. So sine of our angle theta is the ratio of our opposite side to our hypotenuse of our right triangle. Now the cosine of theta, the cosine of whatever this angle is going to be a constant, and that relationship is between the adjacent side of your angle theta and the hypotenuse of the triangle. Tangent is going to be the opposite side over our adjacent side. And then our remaining 3 are simply the reciprocals of those above. So if I wanted to relate, instead of the opposite to the hypotenuse, if I wanted to reverse this and go hypotenuse to opposite, then I would use the cosecant function. If I wanted to relate the hypotenuse to the adjacent, then I would use secant. And if I wanted to go adjacent over my opposite side, then I would use my cotangent. So again, all our trig functions are doing is they are giving us a constant ratio between two sides of our triangles. The opposite and the adjacent sides are always legs, so these sides are always attached to your 90-degree angle, and your hypotenuse is always across from our 90-degree angle. So we're going to go ahead and determine the value of all 6 trig functions for the triangles given below. So here's my angle theta, so I need the sine of theta, the cosine of theta, the tangent of theta, and then the reciprocals of all these. So cosecant is the reciprocal of my sine, secant is the reciprocal of my cosine, and cotangent is the reciprocal of my tangent function. So looking at my angle theta, my sine is the opposite side. So here's my adjacent leg. That's the leg that's touching my theta and the 90 degrees. So the opposite side is the side that's not touching my theta, but is still attached to my 90 degrees. So sine is the opposite over my hypotenuse, which is 13. Cosecant would be the reciprocal of that, hypotenuse over opposite, or 13 over 12. Cosine is my adjacent leg over my hypotenuse. Now, unfortunately, I don't know that length of the adjacent leg, so I'm going to go ahead and call this A, and then I'll use Pythagorean Theorem to solve. So a squared plus 12 squared is equal to 13 squared. A squared plus 144 is equal to 169. So a squared is equal to 25, which means that A is going to be 5. Since we're not in a coordinate plane, we're just talking about a distance here, I have a positive 5 representing that length. So then the cosine is my adjacent leg, which is 5, over my hypotenuse, which is 13. My secant is the reciprocal, so 13, my hypotenuse, over the adjacent, which is 5. Tangent is opposite over adjacent. Well, the opposite leg from my theta is 12. The adjacent leg to my theta is 5. So the tangent function would be 12 over 5, and cotangent would be the reciprocal, which would be 5 over 12. I'll walk us through one more, and then I've got a couple for you to try. So I want sine of my theta, cosine, tangent, and then all of our reciprocal functions, so cosecant of theta, secant of theta, and cotangent of theta. So my sine function is going to be the opposite leg. So here's my theta. The opposite leg is 3 over the hypotenuse. which is unknown. So I'm going to go ahead and use Pythagorean Theorem to find the value of my hypotenuse. So h squared is equal to 3 squared plus the square root of 7 squared. So h squared is equal to 9 plus the square root of 7 squared is 7. H squared is equal to 16, which means that h is 4. So now I've got the opposite side is 3 and my hypotenuse is 4. Cosecant is the hypotenuse, which is 4, over the opposite, which is 3. Cosine is adjacent over my hypotenuse, and secant is the reciprocal, so 4 over the square root of 7. Tangent is opposite, which is 3, over the adjacent, which is 7. And cotangent would be the reciprocal, so square root of 7 over 3. Since my theta is in the same position for this entire question, it's not moving, the opposite side is always 3. My adjacent side is always going to be the square root of 7, and my hypotenuse is always across from the 90-degree angle, so that would be the 4 that I found. All right, your turn. Take a moment, pause the video, and try out these two on your own. First thing I'll do is use my Pythagorean theorem to find the length of this missing leg. So a squared plus 7 squared is equal to 25 squared. So a squared plus 49 is equal to 625. Subtracting 49 from both sides, a squared is equal to 576, which does have a perfect square of 24. So this leg is 24. So then I want sine, cosine, tangent, cosecant, secant, and cotangent. So sine is the opposite. So here's my theta. The opposite leg would be 24 over my hypotenuse, which is 25. So cosecant would be the reciprocal, 25 over 24. Cosine would be my adjacent leg. The leg that's touching theta is 7 over the hypotenuse, which is 25. Secant would be 25 over 7. Tangent of theta, my opposite side is 24, and my adjacent side is 7. And cotangent would be the reciprocal, so 7 over 24. For our second example, to find the hypotenuse h, I've got h squared is equal to 10 squared plus 20 squared. So h squared is equal to 100 plus 400. H squared is equal to 500, which means that h is 10 times the square root of 5 when I square root both sides. So then going through, I find all 6 trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. Sine is the opposite leg, so that would be 20 over the hypotenuse, which is 10 square root of 5. I can simplify to 2 over rad 5. I'm not going to worry about rationalizing. Cosecant is the reciprocal, square root of 5 over 2. Cosine is the adjacent, which is 10 over the hypotenuse, 10 rad 5, which simplifies to 1 over the square root of 5. Secant would be the reciprocal, so just square root of 5. Tangent is the opposite, which is 20 over the adjacent, which is 10, simplifying to 2. And cotangent is the reciprocal, so 1/2. So now let's talk about some specific values. So the cosine of 45 degrees is always going to relate the adjacent to the hypotenuse of a 45, 45, 90 degree triangle, and it will be constant no matter how large or small your triangle is. So for example, I can have a 45, 45, 90 triangle that is about this size, or I can have a 45, 45, 90 triangle that is much larger. The cosine of 45 degrees says that it doesn't matter how large or small your triangle is. If I look at that adjacent side and compare it to my hypotenuse, that ratio is going to be the same regardless of how large or small your triangle is. So let's go ahead and look at a 45, 45, 90 triangle. Any 45, 45, 90 degree triangle has the ratios of A, and then the hypotenuse is whatever that length A is times the square root of 2. So then the cosine of 45 degrees would be that adjacent side over my hypotenuse, which is a square root 2. So the adjacent side is a over that hypotenuse, a rad 2, and then I can simplify down to 1 over the square root of 2. We can rationalize, but we're not going to. We're just going to focus on setting up our ratios. The tangent of 45, again, doesn't matter how large or small your triangle is, it will always be constant, is going to be the opposite side. So in this case, the opposite side is a over my adjacent leg, which is also a. So opposite over adjacent is 1. Now we'll go ahead and look at a 30, 60, 90 degree triangle. In a 30, 60, 90 degree triangle, our ratios are the following. The smallest side is a, the hypotenuse is 2 times a, and then that middle side is going to be a times the square root of 3. So looking at our 30 degree angle, the sine of this angle is going to be the opposite, which is a, over my hypotenuse, which is 2a. So sine of 30 is a over 2a, which does simplify down to 1/2. Cotangent of 60, so I'm going to look at my 60 degrees. Cotangent is the adjacent leg, which is a, over my opposite leg, which is a times the square root of 3, which does simplify to 1 over rad 3, and again, we won't worry about rationalizing right now, we're just setting up our ratios. So it doesn't matter how large or how small your triangles are, your ratios between those two sides for each of your trig functions are going to be constant depending on the angle that you're looking at. So we'll look at the cosine of 135 degrees now. Now unfortunately we can't create a 90 degree triangle with a cosine with an angle value of 135 degrees. So what we're actually going to do is we're going to place this angle in standard position. That means that I'm going to put the initial side on the positive x-axis and put the hinge here at the origin. Then I'm going to open up my angle 135 degrees and we will be left with this angle that is shown here. So if I want to find the cosine of this angle, I need a right triangle. So what I'm going to do is I'm actually going to drop down that terminal side of my angle to form a right triangle. The angle that I made was 135 degrees. Rotating it around all the way to the x-axis would be 180 degrees, which means that this angle that we just looked at is 45 degrees. That's going to be just like the angles that we were talking about on our previous slide. So now what I'm really concerned about is I'm concerned about finding the cosine of this angle of 45 degrees. Since we're using essentially the same angle, we just had to form a right triangle in order to be able to use our cosine values. What's important is that whatever this distance is along the bottom is negative because we are on the negative x-axis, but this y value going up is positive since we are increasing in a positive direction for y. So using my relationships of 45, 45, 90 triangles, I know that this side is a, and my hypotenuse is a times the square root of 2. But this length, since we are talking about a negative x value, is going to be a negative a. So now the cosine that I'm looking at is the adjacent, so negative a over my hypotenuse, which is a times the square root of 2, which will give me a value of negative 1 over the square root of 2. For the sine of 150, I will do something very similar. My 150 degrees will be right about here. To complete that 180 degrees, I would need another 30 degrees, which gives me a 30, 60, 90 triangle. So my ratios then are positive a, since my y values are positive. I've got a negative a times the square root of 3 and 2a. Sine is the opposite side over the hypotenuse. So sine of 150 then, using this triangle that I just made, I have the opposite side of which is a over the adjacent side, which is 2a, simplifying down to 1/2. Go ahead and pause the video and see what you can do with these 5. You can pause the video again if needed to check your answers, but that's the end of our video. Thanks so much for watching.